Hello friends, this is Jim with Science Talk. I have some sad news to share with you. I just learned a short while ago that Wallace Smith Broecker, also known as Wally Broecker, passed away. He was 87, and he has often been called the grandfather of climate change. His contribution to our understanding of geochemical cycling, to our understanding of glaciers, ice sheets, ice ages, and climate cannot be overstated. He was a giant, and he worked until the day he passed away. So, let me give you a brief synopsis of his life, and we'll discuss his important scientific work and his contributions to science. He was born in November 29th, 1931 in Chicago, and he was a Newberry professor in the Department of Earth Environmental Sciences at Columbia University, a scientist at Columbia's Lamont Doherty Earth Observatory. He was there for many, many years, and a sustainability fellow at Arizona State University. It was him who developed the idea of the global conveyor belt you have heard me discuss with you a number of times before, where in the global conveyor belt he links the circulation of the global ocean and made major contributions to the science of the carbon cycle, as well as other elements, and the use of chemical tracers and isotope dating in oceanography. Isotope dating. I've discussed isotopic fractionation, but also we can use isotope dating to determine when things took place and other information. He attended Wheaton College. He interacted with J. Lawrence Culp, Paul Gass, and Carl Turakian. And then after there, he went to Columbia University, where he pretty much stayed there for the rest of his career and life. In 1975, Broecker popularized the term global warming when he published a paper entitled Climate Change, Are We on the Brink of a Pronounced Global Warming? Now, you hear climate deniers say all the time, well, back in the 70s, these guys were calling it global cooling. No. The term global cooling came about because of one irresponsible journalist who did not fact check his or her story and basically put it out there. Even back then, Wally Broecker was stating global warming. Broecker recently co-wrote an account of climate science with the science journalist Robert Kunzik. This included discussion of the work of Broecker's Columbia colleague Klaus Lackner in capturing CO2 from the atmosphere, which Broecker believes must play a vital role in reducing emissions and countering global warming. Now, Broecker has been described in the New York Times as a geoengineering pioneer. That is not accurate. I've discussed with you before what geoengineering really is all about. All he is saying is we need to sequester CO2. That's all he's saying. And develop means to capture CO2. That is not geoengineering where let's have a bunch of DMS into the atmosphere and let's throw a bunch of iron into the ocean and see what the F happens. That's not what he was advocating for. So that is an inaccurate description of him. But when you have non-science people writing about science, this is what happens. So here are some of the areas of research that Broecker did. Pleistocene geochronology, radiocarbon dating, chemical oceanography, including oceanic mixing based on stable and radioisotope distribution. This includes research on the biogeochemical cycles of the element carbon and on the record of climate change contained in polar ice and ocean sediments. Let me repeat that last bit. Biogeochemical cycles of the element carbon and on the record of climate change contained in polar ice and ocean sediments. I have discussed these with you guys before. I did a lengthy video on isotope fractionation. He pioneered this methodology. This is him. Broecker authored more than 500 journal articles, that's peer-reviewed, 17 books. He is perhaps best known for his discovery of the role played by the ocean in triggering the abrupt climate changes which punctuated glacial time, in particular the development and popularization of the idea of the global conveyor belt, ocean conveyor. His contribution went far beyond his coining a conveyor belt term, which has a nice catchiness to it, even though he demonstrated it exists. His work in the foundation of the carbon cycle, application of radiocarbon to paleoceanography are landmarks in the field. He was developing a lot of the technique, a lot of the science. His work with chemical traces in the ocean is integral to modern chemical oceanography. I'm going to go, in a few moments, I'm going to go through some of his books here, a listing of some of his books here. His textbook, Traces in the Sea, authored with Sung Hoon Kang, is still cited in the contemporary literature 35 years after its publication. 30. Came out in 1982. Let me do the math here. 37 years. Okay. Okay. Yeah, came out in 1982. Broecker also wrote about mode changes in the thermohaline circulation, which is what starts the whole conveyor belt process. We have clear evidence, this is a direct quote from him, we have clear evidence that different parts of the Earth's climate system are linked in very subtle yet dramatic ways. The climate system has jumped from one mode of operation to another in the past. We are trying to understand how the Earth's climate system is engineered so we can understand what it takes to trigger mode switches. Until we do, we cannot make good predictions about future climate change. Basically, what he is saying is that until we better understand the system, it's a little difficult to extrapolate too far out. Now, you have to put in mind this quote came out some time ago. This is not a recent quote. The modeling has improved. But his point is well taken. Get better models, make better predictions. Now, when he says how the system's engineers, not talking about human interactions here, he's talking about how the planet itself works. It used to be, and even he at first, when he was developing the conveyor belt type model, used to think that it took to go from an interglacial period to a glacial period, it took some time, like several hundred years. As he did further research and further modeling for the collection of data, etc., he came to realize that switching from, as he says, one mode to another, interglacial to glacial or glacial to interglacial, took literally on the order of decades. As he said, literally like flipping a switch. It's basically his work is why I have come to think that what we're doing now with all the ice sheets melting and all the fresh water being dumped into especially the North Atlantic, and also there is a deep water formation off Antarctica, that this will trigger an ice age because it will shut down the conveyor belt, which is a heat distribution mechanism for the planet. It's his work that has inspired me to come to the conclusions that I have come to. So here's a list of some of his works here. Chemical Equilibria in the Earth, that came out in 1971. Chemical Oceanography, that came out in 1974. And then in 1982, Traces in the Sea. Now, Traces in the Sea is basically a follow-up to Chemical Oceanography. In 1988, he wrote How to Build a Habitable Planet. And then 1995, another really excellent work, The Glacial World According to Wally. And there's a couple others, for example, in 2008, along with Robert Kunzik, Fixing Climate, What Past Climate Changes Reveal About the Current Threat and How to Counter It. How many times have you heard me report to you guys that the key to understanding the present and the future is understanding the past? And that's basically was what he was trying to say in that quote I read to you earlier. In 2010, the Great Ocean Conveyor, discovering the trigger for abrupt climate change. And then as recently as 2016, a geochemist in his Garden of Eden. As I said, the gentleman worked until the day he passed away. Now, I printed out here, because I've got an electronic version of his Traces in the Sea, but I'm just going to go through some of the table of contents so you get an idea of just how comprehensive this work is. It's still seminal. It's, as I said to you earlier, it's still being quoted in contemporary research papers. So, just in the basically it's like 9-10 major chapters here, and I'll read you some of the topics that he covered. Deep profiles of sea salt composition, chemical composition of marine organic matter, composition of particulate matter caught in sediment traps, the distribution of biointermediate constituents, basically things being recycled, estimation of input rates. All right, then in chapter 2 he discusses the sedimentary sink, basically particulate matter sinking through the water column, settling on the substrate, becoming incorporated into the sediments. So he discusses sediment types, the distribution of opal production, distribution of calcite in marine sediments, and the degree of calcite saturation. Okay, there's a thing that chemical oceanographers refer to called the calcium compensation depth, and it has to tie in with calcite saturation. It's an extremely complicated topic with a lot of mathematics and chemistry and etc. So I'm not going to get into it, but it is an important aspect in understanding the oceans. And with the pH, now the ocean being decreased, at least surface water-wise, this could affect the CCD, the calcium compensation depth. Then he has spatial variations in the calcium carbonate saturation of seawater, basically referring to the calcite. Factors controlling the rate of calcite solution. Then in chapter 3, he looks at the atmospheric input, the solubilities of gases in seawater, rate of gas exchange, oxygen deficiencies in the deep sea, oxygen concentration in surface ocean water, the carbon dioxide content of surface ocean water. So you can see where I get a lot of my discussions, a lot of the topics for my discussions with you guys. Chapter 4, he looks at reactive metals. This is where we get into the radioisotope signal. So basically, he was using the isotopic signatures to follow water mass movement. This is how we learned that the ocean doesn't just sit there. The ocean is in motion, horizontally, vertically, combination. It's in movement. Products of uranium and thorium decay. And you know, we at IARC, we were using the Traces in the Sea concept to follow isotopic signatures of water coming from the Mackenzie River as it emptied into the Beaufort Sea. So he looked at the lead, polonium, the lead-210, polonium-210, radium-226, anthropogenetic plutonium in the sea. You know, creating a model of metal transport, distribution of stable metals, stable isotope ratios of reactive metals, iron, manganese transport, etc. Very, very detailed, very complete, and very thorough. Then he looked at the rate of vertical mixing, rate of continental runoff, sediment accumulation rates, radiocarbon dating, uranium series dating, potassium argon dating. These are now common dating methods when you especially want to date something way further back in time. So then he goes, what keeps the system in whack? This is, he did have a kind of a funny sense of humor. Okay, phosphate controls, silica controls, carbon controls, interaction between phosphate and carbon controlled, nitrate controls, dissolved oxygen, anion, cation. Anion are negatively charged ions, cation are positively charged ions. Then he looks at the marine geochemistry of carbon-13, right? In my isotopic fractionation video, I discussed with you carbon-13 as part of that lengthy video. And then we start getting into some important topics that led to his development of the conveyor belt. He looked at the traces for diapycnol and isopycnol mixing. Pycnol is a reference to density changes. So iso means the same density, diap basically means between two different densities in essence. And then here's the sources of deep water. Okay? The northern component water, referring to the Jinsei location. Ventilation of the deep Atlantic Ocean. Ventilation of the deep Pacific and Indian Oceans. This is where we start getting into the conveyor belt. Ventilation doesn't necessarily mean, oh, we got to air the room out. Ventilation means a replacement of the water. For example, if I have a water body of water, and the bottom layer, there's no mixing, no overturn, that bottom layer becomes anostic, it becomes stagnant. Ventilation would be that there is a mixing so that water gets mixed, gets overturned, churned up, maybe even cycled through on a whatever time frame we're talking about. It's called ventilation. Then he has a chapter called the anthropogenic invasion, movement of water through the oceanic thermocline. He looks at tritium, that's hydrogen 3, distribution within the thermocline, temporal trends in the tritium, hydrology of the main thermocline. Now, the main thermocline is basically sometimes referred to as the permanent pycnocline. Thermocline is a sharp change in temperature, but because density of seawater is determined by temperature and salt content, we call it pycnocline, change in density. And that's typically, depending where it's about 1,000 to 1,500 meters deep, as opposed to the seasonal thermocline, which will develop in upper water layers. And I've discussed that with you before, that you need a mixing event to get the nutrients into the photic zone, followed by stabilization of the water column, meaning the development of a pycnocline, so that the phytoplankton stay within the photic zone and they can do their thing. Okay? He's talking about the permanent pycnocline further down. Then he looks at implication of equatorial upwelling on the tritium budget. Then chapter 9 is devoted to ice sheets and ocean phosphate, temperature salinity changes, changes in calcium carbonate storage, changes in phosphate concentration, the combined evidence from deep sea cores, again looking at isotopes. Then we looked at the CO2 record, the oxygen record, glacial to interglacial changes in ocean mixing rate, glacial to interglacial lysocline changes, and then changes in the distribution of nutrients in the deep sea. And then in his last chapter, can man override the control to build up fossil fuel CO2 in the atmosphere and oceans? And he goes through a whole bunch of topics here, including numerical modeling, etc. So, while it is sad that he has passed, let us also celebrate a remarkable person, an amazing career that spans basically 6 decades. And his contribution to science, to oceanography, and to climate understanding cannot be overstated. As I said at the outset, he was a giant. So, Wally, thank you. Thank you for inspiring many other oceanographers to follow in your footsteps.